we're ready to wonder which normal should we use. So remember, we talked about this when we were building our objects, but we haven't used normals yet. You're going to have to use them in this lab. Lighting is all about normals. You see, we have to test in.L, and the reflection vector requires reflecting around the normal. So we're now going to have normals with every vertex. So we said it's mathematically well defined to calculate a face normal. So if I have a surface, I can calculate this normal by looking at the cross product of the three vectors on my triangle. So these are going to create face normals. And I could paste these normals on every vertex. Or I could average the neighboring face normals and get something which is often called a vertex normal. A little bit of a misnomer because we always pass normals at the vertex, but it means the normal which is calculated to be the average of these things. So we could try to get this normal. We can also try to somehow interpolate this normal in between our vertices, although it's not immediately clear where we would do that yet. But we could also try to do that. So we have a bunch of different normals we could use. So this picture of flat shading is using face normals. So you take your triangle, you calculate the real normal for this triangle, and you use it everywhere for the triangle. This yellow dot is the light. The black dots are vertices. It'll get you pictures like this. You'll see clear boundaries of where your triangles were. So Garot shading, Garot is a guy, and he invented this idea that said, okay, we're going to average those neighboring triangles. We're going to calculate our lighting based on these average normals, and then we're going to interpolate the lighting across the surface. That gets you a picture like this. Notice the specular highlight is still a little bit messed up. The next year, Fong, another guy, came along and said, I love Garot's idea, except for he didn't go far enough. We should calculate these in-between normals, and then we should interpolate the normal across the surface. And then we should run our lighting calculation, not at the vertex, but we should instead do our lighting calculation at each pixel with this changed normal. And so that will get you a nicer looking highlight. So this should be the same polygons in all these cases, but we get a nicer looking highlight. So this question of which normal you're using and where do you take that normal and stuff it into the lighting equations? Because I can run my Fong lighting equation that has ambient plus diffuse plus specular. I can do with flat or Garot shading. It's confusing. Fong is a guy. So he invented this lighting model that we're talking about, ambient, diffuse, specular. He also invented this idea that you can interpolate the normal in between. So we see his name in two different places. Okay, the important differences here are we calculate the light at the vertex, meaning we put all the code in the vertex shader, and then we use a varying and let it interpolate the light intensity between the fragments. Here, we interpolate the normal, meaning we stuff the normal into a varying variable and then calculate the lighting in the fragment shader in order to get this kind of effect. And this is what I'm going to ask you to do in the lab. But maybe before I go on, questions about this? Okay, so spotlights can sometimes be nice. We might like to get this kind of effect on our object rather than having the light shine everywhere. So it's fairly easy to do this. If I'm writing the code to calculate lighting, what I can do is I can look at my point and say, is my point within some direction? So if I have a direction to my light, my spotlight pointing direction, when I'm actually calculating my shader, I will have had to pass this direction in along with the light intensity. But then I can just look at this angle. And how do we look at angles? Oh, we typically use a dot product. So we get our direction to our point. Don't forget to normalize it because we always want all our vectors to be normalized. And then we have this D and W vector. We can look at it. And if you're within range, then you can turn on your spotlight. So it's pretty easy to turn on this kind of effect. There was a question of, do we have to do all this low-level math in WebGL, or do we have other tools to put them together? This math is going to live in GLSL. It's going to be in your vertex or fragment shader is where this math is going to end up. So in your JavaScript, you're going to pass in the various vectors and lights, but the actual calculation is going to be done in the fragment shader because we want to do it per pixel to get this nicer kind of highlight. And so we're going to do the calculation at that point. Bump and normal maps are another nice thing that you can do. So if we have some surface that has normals, since lighting is all about the normal, if we just fake the normal, we can fake like the surface has we can fake like the surface has got additional variation that's not really there. So if this is a bump map, the bump map, this is a height field, has some shape like this. If we add the, and we store this thing in a texture, so we do the 2D sampler texture lookup, we get the height, we add that height to the normal that we had on our original surface, and we can reconstruct this fake surface, and then we can get these fake normals, and then we can use the fake normal during lighting. So here's an example of what that might look like. So here's just a texture map like you've done so far. With a bump map, you can make it look a little bit more realistic. Bump map plus lighting. It should always be assumed that a bump map is being used for lighting. Here's some other examples of bump maps. These things are just planes. Here's our teapot, but it looks like a bumpy teapot. There's not millions of triangles in here making it bumpy. There's just a bump map doing it. Bump maps usually look like this. They store a height field. A transform of this is to store the normal. So rather than storing the height, we could store the change in normal direction directly and then apply this. So you'll usually see something that looks like this if you're talking about a normal map. So here's an example of an object with no normal map. The normal map has some variation in it, and then it's creating these details on the surface of being done with a normal map. Here's another example. Here's an original mesh that had 4 million triangles in it. We simplify it down to 500 triangles, but now you can't see any detail. So we store all that detail in a normal map, apply the normal map back on, and then we feel like we see a high resolution mesh that we didn't really see. Often comes up for modeling people. So you'll see something like this, right? Here's the mesh, and then here's the normal map, and then you can get renderings that look like this. Here's a detail of somebody's face. Typically, the model of like where's the nose, where's the nostril, this is all in triangles, but all of these little pores and details that make it look like it's very high resolution, this is typically stored in a bumper normal map. Okay, type your questions or ask them about bumper normal maps if you want. Meanwhile, I have a question about this spotlight and which vector exactly is it that we're talking about. But let me go back to that. So we typically have this W vector is the same vector that we previously calculated and called L. So if we go, let me get this picture I was using. Okay. This picture has everything. Okay, I have a direction from my point to my light. I have a direction from my point to my eye. I have a normal vector. This normal vector, these are going to be calculated because it depends on where my point is, right? Which depends on what my vertex and fragment shader are doing. I have a normal. This is going to get passed in the same way we pass in U and V. So now the question is, what is this direction vector? So that's going to be a vector that says which direction the spotlight is pointing, if we want to do a spotlight. So my spotlight might be pointing in this direction. So this D vector will be pointed whichever way is the spotlight. This W vector that I'm using to test is just in the opposite direction. The one we were previously calling the L vector went from P to light. And here we're doing it this way just because we're comparing this angle. And so you want to get the directionality of the vector right. I don't know if this is making it completely clear. You don't have to do a spotlight in your assignment, by the way. I see another question about what's the color in these bump maps, in this normal map. Okay, when I store a normal map, in a bump map, I store a height field. It's a scalar value for the height of the surface. For a normal map, we have a normal that has an XYZ direction. It's a vector. And so we re-encode the XYZ into the RGB components when we view it as a texture map. So we just store an image, and when we read out our texture map for RGB, we stick those things into normal XYZ, is the idea of how do you use this. There's some more details about getting normal maps to work the right way. So you have to know something about the tangent space of the object and how to modify the underlying normal. But I think the easiest conceptual way to think of it is, instead of using the normal passed in with the triangle, you're basically looking the normal up in a texture map and then just applying that normal to the surface. I think that's the conceptually best way to think about what's going on. Okay, let's talk about where we're going to actually do this in our code. Let me take a quick look of what do I think I have remaining. I see we're getting close on our time. And then we go to administrative. Okay. No. Okay. WebGL. Okay, this is example taken from the book. So the first thing to notice, the book swaps around the way it uses its matrices. So the book has something called an MVP matrix, model view projection. So that's model view projection. So we've written in our code, and you should keep writing in your code, separate model view and projection matrices. I think it'll make your life good. When I'm calculating the final position that this thing is going to land on the screen, I need all of these matrices. However, when I want to know the world coordinates position of my object, right? So I've taken my cube, I've rotated it and translated it to make the arm of my creature. I don't care about the projection and viewing. It's nothing about the camera. I'm trying to find the world coordinate space. So the world coordinate space is my A position, the same one I used up here, times only the model matrix. So I'm leaving out the view and the projection matrix. So I need this in order to find the point in world space for calculating my lighting. Normals actually require yet another matrix. I'm going to refer you to the book for this. It's a magic matrix. Things will look okay, actually. If you leave this out, you probably won't be able to tell the difference. But it makes things actually correct when you've transformed your object. If you have a cube that's never been transformed, in fact, this will just be identity. But if you've transformed or rotated your cubes or spheres or whatever, then this will come into play. Anyway, you use this matrix to multiply times the normal, not the model matrix. See the book for the details of what's going on exactly and how do you calculate that thing in your code. We have a bunch of varying variables. These are all the things that are going to be passed to our fragment shader and interpolated. So each of these will be interpolated separately. Notice we're passing the normal because we're going to do the final lighting calculation down here in the fragment shader. Why are we normalizing the normal again? We already normalized the normal up here. So we normalize the normal again in the fragment shader because the interpolation might mess it up and it might not be unit length anymore. So our light direction is just the light position minus the position of the surface we're dealing with, right? That's why we solved for it up here so we could use it. So that gets us a light direction. Here finally is our n.l, diffuse shading that we talked about. Here's our n.l. And then we have a light color and we have a triangle color. So this is being passed in as an attribute. The light color is being passed as a uniform in this case. And then our final answer is diffuse plus ambient. In your assignment, you're going to need to add specular to this also. So a lot of the setup of getting the lighting set up, you'll be able to find an example in the book, but there's a little bit of extra calculation.